In this lecture, we shall consider inelastic collision and in particular ballistic pendulum and collision in 2 and 3 dimensions. If a collision is inelastic, then by definition the kinetic energy is not conserved. The final kinetic energy may be less than the initial kinetic energy, the difference being ultimately converted to heat or to potential energy of deformation in the collision, for example. The final kinetic energy may exceed the initial value as when potential energy is released in the collision. In any case, the conservation of momentum still holds, as does the conservation of total energy. Let us consider finally a completely inelastic collision. The two particles stick together after collision so that there will be a final common velocity Vf. It is not necessary to restrict the discussion to one-dimensional case. Using only the conservation of momentum principle, we find that before collision the total momentum is m1 v1i plus m2 v2i is equal to m1 plus m2 into vf, where vf is the final velocity after collision, because the two particles they are stick together, so the common velocity will be obtained from this relation. And we now consider ballistic pendulum. In the ballistic pendulum, we have this kind of situation. And a ballistic pendulum consists of a large wooden block. This one is the wooden block of mass capital M, suspended by cords. When a bullet of mass small m with velocity vi fired into it, the block swings, rising a maximum distance y. Say this one will swing this way. And let us suppose this vertical height is y. The ballistic pendulum is used to measure bullet speeds. This vi can be determined from this ballistic pendulum. The pendulum is a large wooden block of mass capital M hanging vertically by two cords. A bullet of mass small m traveling with a velocity vi horizontally strikes the pendulum and remains embedded as shown in these figures. If the collision time, the time required for the bullet to come to rest with respect to the block, is very small compared to the time of swing of the pendulum, the supporting cords remain approximately vertical during the collision. Therefore, no external horizontal force acts on the system, and here the system means the bullet and the pendulum. during collision, and the horizontal component of momentum is conserved. Horizontal component of momentum is conserved. The speed of the system after collision is Vf. After collision is Vf is much less than that of the bullet. Says this Vf is very, very smaller than Vi. This is before collision. The final speed can be easily determined so that the original speed of the bullet can be calculated from the momentum conservation. The initial momentum of the system small pi is mass into velocity of the bullet mi, and the momentum of the system just after collision is pf, which is equal to mass of the bullet plus mass of the pendulum into velocity vf. This is the common velocity after collision, so that the conservation of momentum gives, okay, let us suppose this is equation 1, this is equation 2. So conservation of momentum gives pi equal to pf. Okay, before collision, the total momentum of the system must be total momentum of the system after collision. We equate these two, equation 1 and 2, then mvi equal to m plus capital mva. So this is equation 3. After the collision is over, the pendulum and the bullet swing up to a maximum height small y, as we have denoted here. This y, vertical distance, swing, when the pendulum swings, and the pendulum contains the bullet, where the kinetic energy left after impact is kinetic energy after collision. Kinetic energy will not be conserved in inelastic collision. This is actually an example of inelastic collision. Kf equal to half m plus capital M Vf square. And the gravitational potential energy is Ug, which is mass into says mass is m plus capital M into acceleration due to gravity, and the height is y. Okay, here the kinetic energy will be converted to this potential energy, gravitational potential energy. We have from energy conservation K will be equal to Ug, gravitational potential energy. Now we equate these two. Equate 4 and 5, then we'll have equal to small m plus capital M G Y. Okay, from this equation 6 and equation equation 3, we can eliminate Vf. Okay, equation 3 again, I will show you this equation 3. We have Vf here, and equation 6 we have Vf here. So if we eliminate this Vf, then we can find an expression for Vi, and which will be given by this. This is equation 7. Now, hence we find the initial velocity of the bullet. Can be obtained from this relation. Now these are known: small m, capital M, acceleration due to gravity is constant, and y is the vertical distance for the swing of the pendulum. So we can easily then calculate Vi from this relation. Now we want to find the ratio of kinetic energy before collision and after collision. Now the initial kinetic energy of the system before collision kinetic energy of the system before collision. Let us say this is, and there was no motion of the pendulum, only the bullet, and it has kinetic energy small m v I square, and the kinetic energy of the system after collision is Kf, which is half small m plus capital M Vf square. And in this inelastic collision, kinetic energy will not be conserved, so Ki and Kf are not equal, and we can find the ratio Kf by Ki will be equal to and if we substitute the values of Vf and Vi from previous equations or relations, we will have this. You see the numerator is much smaller than the denominator. That means initial kinetic energy is much greater than the final kinetic energy. For example, if you give an example, uh, if say the bullet has mass 5 gram and the pendulum has mass 2000 gram, means 2 kg, then this ratio kf by ki equal to 5 divided by 5 plus 2000, and this one is around 0.01, which is 1%. 1%. That means final kinetic energy is only 1% of the initial kinetic energy. Where this kinetic energy actually went, and 99% of the kinetic energy is converted to other forms of energy such as heat. The velocity of the center of mass of two particles is not changed by their collision, for the collision does not change the total momentum of the system of two particles, only the distribution of momentum between the two particles. The momentum of the system can be written as P equal to, say, if we have two masses M1 and M2, and this is velocity of the center of mass. This is a new topic actually. This is about collision in terms of center of mass. If no external forces act on the system, then the linear momentum is constant before and after the collision, and the center of mass moves with uniform velocity throughout. If we choose a reference frame attached to the center of mass, then this center of mass reference frame VCM will be 0 and the momentum will be 0. There is a great simplicity and symmetry in describing collisions with respect to the center of mass, and it is customary to do so in nuclear physics. For whether collisions are elastic or inelastic, momentum is always conserved, and in the center of mass reference frame, the total momentum is 0. These results hold in 2 and 3 dimensions as well as in 1 dimension, because momentum is a vector quantity. Okay, now the last topic, we'll give just an overview of this, the collisions in 2 and 3 dimensions. in 2 and 3 dimensions, except for a completely inelastic collision, the conservation laws alone cannot tell us the motion of particles after a collision if we know the motion before the collision. For example, for a two-dimensional elastic collision, which is the simplest case, we have 4 unknowns, namely the 2 components of velocity for each of 2 particles after collision. But we have only 3 known relations between them, one for the conservation of kinetic energy and the conservation of momentum relation for each of the 2 dimensions. Hence, we need more information than just the initial conditions. When we do not know the actual forces of interaction, as is often the case, the additional information must be obtained from experiment. It is simplest to specify the angle of recoil of one of the colliding particles. Let us consider, for simplicity, a two-dimensional case. Let us suppose we have a particle here at rest, and we take the mass of the particle is m2, and a particle is coming towards particle of mass 2, and this particle has mass m1, and it has velocity, say v1I. Okay, and up when this particle m1, okay, let us suppose that this is at rest, particle 2 at rest, and this is say x direction and this is y direction. We are considering two-dimensional case, so the experiment is being done on a plane, and after collision, let us suppose that particle 2 is moving along this direction, is m2 with velocity v2f, and particle 1 is moving along this direction with a velocity say v1f, and this angle is theta 1 and this angle is theta 2. Let us consider what happens when one particle is projected at a target. This is the target particle, we call it target particle. This case is not as restrictive as it may seem, for we can always pick our reference frame to be one in which the target particle is at rest before the collision. So this particle is at rest before the collision. Much experimental work in nuclear physics involves projecting nuclear particles at a target which is stationary in the laboratory reference frame. In such collisions, because of momentum conservation, the motion is in a plane determined by the lines of recoil of the colliding particles. The initial motion need not be along the line joining the centers of the two particles. The force of interaction may be electromagnetic, gravitational, or nuclear. The particles need not touch. Strong forces which act at relatively close distances of approach and for a time short compared to the observation time deflect the particles from their initial courses. This typical situation where we have considered no impact parameter, that means this is head-on collision. Okay, we have the momentum conservation along x direction, and particle 2 was stationary before collision, so this is 0. And this one, the momentum component of particle 1 after collision, this is 1f, and this is cos theta 1, and this is particle 2 m2 v2f cos theta 2. Okay, this is along x direction. The momentum conservation along x direction, and in y direction the momentum conservation equation. Okay, along y direction we have 0 because the particle with mass m1 was moving along the x direction, and the particle 2 is stationary, so we have 0 linear momentum before collision. And after collision, the y this is a y component of particle 1, this is mass 1, particle 1, mass m1, so is minus m1 v1f sine theta 1, and this is plus m2 v2f sine theta 2. So we have these two relations from momentum conservation, and our consideration is the collision is elastic collision. So for elastic collision, kinetic energy will be conserved. Therefore, we have an equation for conservation of kinetic energy. So half m1 v1 I square, and 0 because particle of mass 2 was at rest before collision, and after collision is 1/2 m1 v1 f square plus 1/2 m2 v2 f square. If we know the initial conditions m1, m2 and v1I, we are left with 4 unknowns: v1f, v2f, theta 1 and theta 2. But only 3 equations relating this. We have this equation 1 and this equation 2, and this is third equation. We can determine the motion after collision only if we specify a value for one of these quantities. Let us consider that this one of these quantities is the theta 1 is known, say, for example. Then we can easily find the other 3 variables. Okay, we are not going to discuss further details of collisions in 2 and 3 dimensions. And this is the end of part 3 of chapter 1. We are left with the problems relevant to the topics that we have studied so far. This chapter actually gives some problem in part 4, and the student should solve these problems. Okay, this is the end.